So let's get started with stoichiometry and the mole, lecture number 10. I wanted to start out by talking to you guys about some quarter 2 objectives, just some general things I want you guys to get out of quarter 2 as we go forward in lectures and labs and lab reports and all that. I want you guys to start using my lab report format. That's going to start with the copper cycle lab report, which we're going to do next week after Thanksgiving. I also want you guys to start working toward being a lot more independent. So whether your lab partner is present or not, you have to be able to do and perform the lab by yourself and answer all the questions independently of them, because during quarter 3, we won't have lab partners anymore. Okay, so that's going to be a really big leap for some of you. For others, I think it will be just fine for you to have the ability to do the lab on your own. The other thing too, I want you guys to be thinking, science-mindedly. So to really think about things in terms of science and then making the connection as a scientist to the real world. So, it's not just chemistry. There's, chemistry in life and chemistry every day that you do things. So I want you guys to think in terms of a scientist as you're going about your day-to-day activities, to really think about stuff that's going on. And the other thing I want you guys to be working on is lab skills for quarter 2. We're going to be starting to do, the copper cycle can be difficult to get it correctly. So I've been watching you guys, I'm grading you guys on each part of the copper cycle that you do, each reaction or conversion that you do. I've been watching you and marking grades down for each individual person and how you guys are doing in the lab. So it's important that you guys build up your lab skills as we go through quarter 2, so that when you're working independently for quarter 3, you can handle doing all these things and you know what a crucible is or what a ring stand is. Okay? Another thing I want you guys to think about while you're watching this lecture and while you're watching any future lectures that we do is to think about the connection between the lectures that I send home and the labs and lab reports and worksheets that we do in class. It's really important for you guys to connect the information that I give you in these lectures, which is a lot of definitions and basic ideas and concepts, but then we're going to be implementing those concepts and definitions in the labs. So for you to make the connection between those two is really going to be the way that you ace this class, and especially ace this quarter. I feel like I've said this before, but I really just want to reiterate it because I want you guys to have the connections. I don't want you to just go home, watch the lecture, take notes because you have to, and then kind of toss them aside and do the lab. Those notes that you take are going to be really beneficial for labs and lab reports. From the previous lecture, from lectures 9A and B, I posted 7 questions for you guys to attempt. What I'm going to do when we get back from Thanksgiving break is post those answers on the classroom wall. I want you guys, I'm not going to grade them, they're for your benefit and to know whether or not you did them right. So I want you guys to check them when you get a chance. I'm also going to post other things. I'm going to post the aqueous solutions key eventually. I'm going to post a lot of things as you guys go through them so that you know after the fact what concepts I was looking for. Okay, so anyway, if you guys don't understand a concept, if there's one of those 7 questions from lecture 9A or 9B, if you didn't understand a concept or why one of the equations was balanced a certain way or why it was a combustion and not a synthesis reaction, you've got to come and see me. I'm available in the morning, usually by 7 o'clock, if not earlier, sometimes 6:30. I have prep white block 2 and blue block 4. I also have a study hall during white block 3. And I'm usually after school until at least 3 o'clock, if not 4 or 5 o'clock some days. Come and see me, okay? The whole thing is, these lectures go home so that I have time in class to talk to you, but I'm also available at these other times. So make sure that you guys find time to come and see me if you don't get it, because I'm not going to grade it, and I want you guys to make sure that you're getting everything out of it that you can. In this lecture, I wanted to take a little time to review a few of the types of reactions again, to show you some videos from my favorite guys. I have another video from 1986 that I wanted to show you guys of a couple different reactions. So anyway, the types of reactions are synthesis, decomposition, single replacement, double replacement, and combustion. I just want you guys to be thinking about these as we go forward. I'm always going to be asking you, was this a synthesis? Was this a double replacement reaction? All of the reactions you did in the aqueous solutions lab, if they produced a precipitate, were double replacement. The first type of reaction I want to talk about again is the synthesis reaction, where one thing plus one thing makes one new thing. Okay, so you have multiple reactants and they become one product. Okay, some of you may have heard about, back in, I think it was January of 1986, you may have heard about the Challenger explosion where 7 astronauts went up in the manned mission to space and the whole aircraft exploded. Okay, I was not old enough to remember this, and none of you are old enough to remember this at all, but if you've heard about it, it's a huge tragedy. It's actually based on a synthesis reaction. Another significant piece of this is the woman who is one over from the left in the back row. Her name's Krista McAuliffe. She was going to be the first teacher in space as part of the Teacher in Space program from NASA, but she actually never made it to space because they only got up to about 60,000 feet, I think, which is not technically space. But it's a really fascinating thing to think about, the fact that it was a simple synthesis reaction that caused the explosion, and it's a ridiculous tragedy that 7 of them had to lose their lives because an O-ring sealed off liquid oxygen from liquid hydrogen. It was broken, or it didn't seal right. They were flying in January, so it was really cold. It didn't seal right, something like that, or it broke because it was too cold. And hydrogen and oxygen combined. And so when that happened at the high temperatures that they were heating the engines at, it caused vapor to turn into fire and explode the whole thing. So it was actually a very simple synthesis reaction that caused NASA to revamp its entire space program. It set them back 10, 20 years because of this whole tragedy. But just wanted to share that with you guys.
SRB hydraulic power units have started. T-minus 21 seconds, and the solid rocket booster engine gimbal now underway. T-minus 15 seconds. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Control program. Challenger. Good roll program confirmed. Challenger now heading downrange. Engines beginning throttling down now at 94%. Normal throttles for most of the flight, 104%. We'll throttle down to 65% shortly. Engines at 65%, 3 engines running normally, 3 good fuel cells, 3 good APUs. Velocity 2,257 feet per second. Altitude 4.3 nautical miles, downrange distance 3 nautical miles.
So the 25th Space Shuttle mission is now on the way after more delays than NASA cares to count. This morning it looked as though they were not going to be able to get off.
1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
Looks like a couple of the solid rocket boosters blew away from the side of the shuttle in an explosion.
Flight controllers here looking very carefully at the situation.
Another type of reaction is the decomposition reaction, where one reactant, one thing breaks down and forms multiple things. So for example, I'm going to show you guys a video of hydrogen peroxide decomposing into water and oxygen gas. Okay, and they're going to talk about an enzyme or a catalase, something that speeds up a reaction. So they're going to use something else to make this go faster because hydrogen peroxide doesn't actually decompose very quickly without any help.
All right, I want to show you today a decomposition reaction. Now remember, a decomposition reaction, you start with one thing and it breaks apart into multiple things. So the chemical I brought with me today is hydrogen peroxide, okay? This is the stuff that you can just buy at City Market or King Soopers or whatever your local grocery store is. I'm going to pour that into a test tube. Now, hydrogen peroxide kind of by itself decomposes into water and oxygen gas. So it's actually decomposing right now, but it's a very, very slow reaction. So I'm going to add something to it that should speed up the reaction. This is not a part of the reaction. It's what we call a catalyst. And the catalyst we use will be manganese dioxide. So I'm going to get a small amount of this. Now, one of the products of this reaction is oxygen gas. Okay, so it's a little black powder. I'm going to put it right here. Because one thing about oxygen gas is that it's highly flammable. So I'm going to take a match and light the match, if I can light a match. And I'm going to light this little stick here, a wood splint, so that after this reaction takes place, where do matches go, Mr. Sams?
On the floor.
On the floor. Okay, it's the safest place to put them. So I'm going to add this. This should produce oxygen gas. And then watch what happens when I put this in here. See how it lights up much brighter? That's because we are producing O2 gas, and there's not a whole lot. See, it stays lit even when I put it in there because it's producing this oxygen gas.
You can even blow it out and make it glow and turn it in there, and it'll turn back on or reignite. Hey, look at that.
There you go. See how that's pretty cool? Should do it again. Because it's producing the oxygen gas. And actually, this is a combination reaction and then a decomposition reaction at the same time. We're decomposing the hydrogen peroxide to produce the oxygen gas, and as I produce the oxygen gas, we're actually having a combination reaction. Hydrogen plus oxygen makes water. So pretty cool. All right, this is interesting one. You have A plus BC.
Mm-hmm.
So this BC will be an aqueous chemical, almost always.
Yeah.
And there might be some exceptions, but
Yeah. For our purposes.
for our
they're
purposes,
gonna
they
be-
will
yeah.
always be. So you've got some. Usually, it's an element. Actually, not it's an element plus some chemical BC, and it basically A decides he likes C better than B does, and B gets kicked out.
Yeah.
Okay, we'll use an
There's
analogy.
a
on that.
life lesson in here.
Yes, indeed. Yes. Okay. So here we have an example. If I take iron and I react it with silver nitrate,
Mm-hmm.
it's going to react. And what's happened is the iron's going to say, you know what, I like nitrate better than silver, and so he kicks them out
Yeah.
and says, sorry, you don't get to stick with
No.
nitrate no more. And then iron connects with the nitrate, and then the silver gets kicked out.
Yeah.
So yeah.
There it goes. Okay, what I want to demonstrate for you now is a single replacement reaction. Now in a single replacement reaction, we start with an element. In this case, we're going to use copper, solid elemental copper, so just plain old Cu, solid. We're going to add that to an ionic compound. This is silver nitrate, AgNO3. Okay, so we have a metal ion and we have a metal atom. All right, so we're just going to pour some of this into our little dish here. Just enough to cover the copper. So it's kind of expensive, so don't put too much in. And we're going to put our copper in here. Now this one doesn't react instantly, but in a few minutes you'll see that some silver is forming on the outside of the copper. I'm actually going to add a little bit more just to cover it all up. Yeah, but you can start to see it's no longer that shiny copper color. It's starting to turn into kind of a darkish color. That's actually silver that's forming on the outside. What we're going to do is we're going to stop this. We're going to come back in a couple minutes. We're going to see what that looks like. All right, it's been about 20 minutes since we started our single replacement reaction. So let's take a look and see what we have here. So you can see that a lot of the silver that was in the dissolved solution in that clear and colorless liquid came out of the solution. It replaced the copper. So what it did is some of the copper that was on the copper metal became copper ions, and then the silver ions in solution became silver metal in the single replacement reaction. So you can see on here there's actually coated with silver. Ooh, you can see really well there on the back side. That's pretty cool.
Sam, why don't you put that on that little piece of paper maybe, and I bet it'll flake off. Try and tap it.
Some of our silver metal there on the paper. Chunks of silver.
So if we were to collect that silver, Mr. Sams,
Oh,
we
yeah.
could make a ring out of it.
We
something.
could, or take it down to your local pawn shop and make some money.
Yeah, there you go.
In this economy.
There you go.
It's why silver nitrate's so expensive, because it has actual silver in it. There you have it. Single replacement.
You guys may remember this aluminum chromate. Liz and I made it a while ago to compare aluminum as an element to aluminum in a compound as part of a compound. This is the same product. I saved it so you guys could, so I could look at it later and save it forever, even though it's toxic. No, I'm not going to eat it. You guys don't eat chemicals either. Aluminum chromate, it's formed from a double replacement reaction where we start with something like aluminum sulfate and potassium chromate and ended up with aluminum chromate because the two of them, when they combine together, become insoluble in solution and precipitate out as a solid. Cool. Now, I just want to say again that a double replacement reaction is where two ionic compounds in solution come together and form a precipitate. Now, they don't necessarily have to form a precipitate, but when they do, it's very obviously a double replacement reaction because you know that two of the ions decided they wanted to be with different dance partners. Okay, so if a precipitate doesn't form, then really a double replacement reaction hasn't occurred because the partners don't really prefer to be with anyone else. They just will sit around in solution as ions because they don't really prefer to be with one positive charge or negative charge or anyone in particular. So they'll just kind of sit in solution until you evaporate it or try to separate it again. Now, if you're listening to this, then you know that I'm telling you that this problem here, cadmium nitrate plus sodium sulfide, is an extra credit problem. If you solve this and balance it correctly and bring it into me, I will give you 10 extra credit points. An important thing I wanted to cover with you guys in this lecture is atomic theory. John Dalton, in about 1803, said that atoms of different elements combine in simple whole number ratios to form chemical compounds. He, his big theory was a lot about the fact that elements or atoms combine, they separate, they rearrange in chemical reactions. Okay, so they combine in many different ways, and they combine in whole number ratios. So that was one of the first theories that came up about atoms and how they perform, how they behave in chemical reactions. Prior to that, Proust's law was discovered in about 1794. It's actually known to us as the law of definite composition or the law of definite proportions. In other words, it says that every pure compound has its own characteristic element composition, and the proportion of masses will always be the same. We looked at the law of definite composition in terms of how magnesium combines with oxygen. And we found out a lot of us, not all of you came up with the best proportions of elements. It actually combines in a mass ratio of 1.52 grams of magnesium per 1 gram of oxygen. And so not all of you reacted it perfectly or completely, and that's fine. But through many, many years of testing, Proust came up with this law after looking at copper and chloride a lot. What's really interesting is how he went about proving it. He came up with this idea and, late 1700s, like 1794, wrote up the paper, said, I'm sure that atoms combine in specific ratios in chemical compounds. They always combine the same way. I'm 100% sure of it, guys. But this guy, Claude Berthollet, kind of had a lot of clout back then, was a really big guy, had a different opinion, and so Joseph Proust, his theory was just kind of like pushed aside because it was like, no, actually this guy kind of thinks that it's the other way, so you're wrong. Just whatever, you're wrong. It actually took until about 1811 for Claude Berthollet and others to say, oh, well, I guess you have a good point. You're right, and we'll accept it as the law of definite composition. Whatever. Something we haven't talked about yet is the atom, and I think that you guys have probably heard about the atom. If I asked you, what is an atom made of? Protons, neutrons, and electrons. After some probing, you guys might come up with that answer on your own. Another question I want to ask you guys, and to write this answer down for yourselves, what part or parts of an atom make up the most of its mass? Is it protons, neutrons, electrons, or some combination of the two, or three, sorry. I want to go over a couple of more terms with you guys, atomic number versus atomic weight. Looking on the periodic table, which I'll put up a little picture for you, The atomic number is just the number of protons in an element. It defines the element. So if there's 1 proton, then it's hydrogen because hydrogen has 1 proton. If there's 6 protons, then it's carbon because carbon has the atomic number of 6. Atomic weight, though, is the average atomic mass of each element, which, if we're looking at the atom, the nucleus contains the neutrons and protons. So the mass of an element, for example, carbon, it has 6 protons and 6 neutrons, so its atomic mass is going to be around 12. We actually, as chemists and scientists, we've decided that we base everything around carbon, and so carbon is exactly 12. And so everything else kind of falls around that based on carbon being exactly 12 grams or 12 AMUs or whatever. So another example would be oxygen has 8 protons and 8 neutrons, so its atomic mass is going to be around 16. So atomic mass is usually measured in AMU or atomic mass units. 1 atomic mass unit is roughly equivalent to the weight of 1 proton or 1 neutron. 1 proton is a smidgen more than an AMU. It's about 1.008, and 1 neutron is about 1.007. So they're really close. We kind of just say that it's 1 for our purposes. 1 AMU equaling 1 proton or 1 neutron is going to be just fine. I want you guys to look at grams versus AMUs in terms of size. So 1 proton is equal to 1.0073 AMUs. But 1 AMU is equal to 1.66 times 10 to the negative 24 grams. It's a very, very tiny thing. We know that protons and atoms are very, very tiny, so it makes sense that an AMU is a very, very small unit. 1 gram actually contains 6.022 times 10 to the 23rd AMUs, which is a huge number. See if I have here my college text. They have, 6.02 times 10 to the 23rd marbles. If you spread them over the entire surface of the Earth, it would produce a layer about 3 miles thick. Another one is if you took 6.02 times 10 to the 23rd pennies and you place them side by side in a straight line around the Earth, they would encircle the Earth 300 trillion times. Okay, so one of the things we have to do is make the leap from law of definite composition in grams to law of definite composition in terms of stoichiometry. Now, that sounds like a big word and crazy, and maybe it's going to be really difficult, but it just means to measure elements. It's from 2 Greek words, stoichion and metron, So we're just measuring the amount of elements in something, just like we've done already with things in terms of grams. Write this down. Stoichiometry is used for the proportions of elements in compounds. In stoichiometric compounds, the proportions are whole numbers. So if you think about this, we've started writing and balancing chemical equations. So in stoichiometric compounds, the proportions are whole numbers, which means that when you're balancing the equation, you're saying that one hydrogen combines with 1 oxygen. That's not even right. 2 hydrogens combine with 1 oxygen to make a molecule of water. All right, it's getting a little late at my house. I apologize for not being able to think of that right off the top of my head. But anyway, if it was 1 hydrogen and 1 oxygen, and that made 1 molecule of water, H2O, you know that that's not a balanced equation. And to balance that, you have to do that with whole numbers. Okay, so stoichiometry is how we balance equations, and it's used to predict quantities in a chemical reaction. So what I want to do is show you guys a little video with an analogy by me about stoichiometry. So, in the spirit of the holiday coming up, I'm going to give you guys an example of stoichiometry in terms of making green bean casserole, which, as I know how to make it, we take 1 can of cream of mushroom soup, plop it in there just like that, yum. 1 can of green bean soup, or cream of mushroom soup, about half a cup of milk. Mix that up a little bit. 2 cans of French cut green beans. Yum, yum, yum. 1 and 2. We stir that up real good. This is, I never used to like cream of mushroom soup, but definitely like it in a green bean casserole. So I mix this up real good. And then we're going to end up using all of the French fried onions. We're using half of them to start. You know, I mean, this isn't, I'm not trying to give you guys a recipe for green bean casserole. I'm trying to give you an example of stoichiometry. So it's going to end up being the whole thing, but half to start. Mix that in there. Pretty good. I don't know if you guys can see it, but it's looking pretty good in there. Mix it up a little more. Oven's ready to go. So I'll toss it in. Uncovered. And we'll be back later for when it's cooked. You found that magnesium and oxygen combine in a ratio of 1.52 grams of magnesium per 1 gram of oxygen. This is by mass. So in terms of stoichiometry, you know, if we need 1 can of green beans for every 2, well, no, that's not how I did it. It was every 1 can of cream of mushroom soup per every 2 cans of green beans. In terms of stoichiometry, you're going to need 1 atom of magnesium per 1 atom of oxygen, or the balanced formula that you came up with, magnesium oxide, MgO, 1 and 1. In stoichiometry, we work with moles of a substance. So at the same terms, 1 mole of magnesium combines with 1 mole of oxygen for a molar ratio of 1 to 1, but a mass ratio of 1.52 to 1. So what's a mole? The Wikipedia definition is a unit measurement that expresses the amount of a substance equal to the quantity containing as many elementary units as there are atoms in 12 grams of carbon-12. Yeah, probably a little confusing. I'll take a second right now to tell you guys that this is a lecture, at least from this point on, that you want to watch a couple times, okay? It took me a really long time to understand the concept of a mole, and I have been through a minor in chemistry, and so it takes a long time to really get it. So I want you guys to really put an effort into understanding what a mole is and what that number means. Now, a couple questions you might be asking yourself from that definition is, what is carbon-12? What is an elementary unit? And how many elementary units of carbon are in 12 grams of carbon-12? So let's look at carbon-12. It's the isotope or form of carbon that has an atomic weight of 12 AMUs. Okay, so in other words, it has exactly 6 protons and exactly 6 neutrons. Okay, like I said before, scientists say that it weighs 12 AMUs, period. That's just what we said carbon weighs. There are other isotopes, other forms of carbon that have a couple more neutrons, a couple less neutrons. They're all out there. So, but it has exactly 6 and 6, and so we say that carbon-12, this is what we're using for our mole definition. Okay, an elementary unit is an atom, molecule, electron, isotope, ion, or other particle in the system. So let's see, for example, 1 mole of water, 1 mole of marbles, which I said would wrap around the Earth 3 miles thick. Okay, so it's the amount in a system. So for carbon-12, we're talking about the individual atoms of carbon-12. What's interesting is that we've already mentioned this number before when we're talking about AMUs and the fact that there are 6.022 times 10 to the 23rd AMUs in 1 gram. Okay, so wrapping your mind around this is going to be difficult, like I said, but we call it, scientists named this Avogadro's constant after this guy, Avogadro, an Italian scientist. But the number, after bazillions of experiments, they came to figure out that there are 6.022 times 10 to the 23rd carbon-12 atoms in a 12-gram sample of carbon-12. Okay, if this number applies to how many objects of something there are in 1 mole of a sample. So 1 mole is equal to 6.022 times 10 to the 23rd objects. Okay? It will always equal that. This is like saying that 1 dozen is equal to 12 eggs, or 1 gross is equal to 144 things. Okay? Think of other examples that help you. The other thing, remember this number. Okay? 6.022 times 10 to the 23rd. Memorize that number as 1 mole. Okay, here's where things might get a little hairy. Again, in a 12-gram sample of carbon-12, there are exactly 6.022 times 10 to the 23rd atoms. Okay, the same is true for any sample of any element. In a 19-gram sample of fluorine, there are exactly 6.022 times 10 to the 23rd atoms. Okay, let's think about it. Let's flip to my front page here. Okay, so when it says 19 grams or 12 grams, how is that related to their atomic mass? Okay, we know that carbon-12, 12 grams is actually equal to the 12 AMUs. So the same is true for the fluorine that's 19 grams. Its atomic weight is 18.99 or 19 AMUs. So just come across, let's see, sodium is 11. Its atomic number is 11, so its atomic weight is actually about 23 AMUs, which means in a 23-gram sample, there are going to be exactly 6.022 times 10 to the 23rd atoms. Okay, it's a pretty crazy number. The big question in all this is, how are the mole and AMUs and grams all related? Okay, it has to be the big question on your mind right now, and I know it was mine. I did not get it the first time around back in high school when I think I took advanced chemistry. I don't remember. It was way different back then, and that was only like 10 years ago. So, but I know that I knew the number was 6.022 times 10 to the 23rd, but that's pretty much where it stopped. So, what I want you guys to do is think about this question. Okay, think about it over vacation while you're eating some turkey. What I'm going to do is, in the video description of this video that I'm sending you, I'm going to give you an assignment. You get an element, and you have to define that element in terms of AMUs, grams, and moles. Okay? Now, it's not as simple as it sounds, because I'm going to ask you individually if you truly understand the relationship between AMUs, grams, and moles. So this is your homework. Okay? I think I'll be checking it at the end of the week that we come back. So Thursday, Friday when we come back, probably Wednesday, Thursday, actually. That'll be like I'm not looking at a calendar. I'll figure it out. But I'll be checking that. I'll be talking with each of you about your element. Okay, that's going to be in the video description. So if you see your initials XY and it says rhenium, that's your element, and you have to define it in terms of AMUs, grams, and moles. Okay, I hope that this hasn't been super confusing. I'm probably going to do a follow-up video. Yeah, so I'll be doing some other things to follow up with this so that we can really practice with moles and get into molar mass and all that. So I hope you guys had a wonderful Thanksgiving. Hopefully you're watching this before. Maybe you'll watch it after. Just have a good Thanksgiving. Don't be mean to your families or anything. Be thankful. Okay, bye. Come here, Christmas kitty. Come here, Christmas kitty. Look at my Christmas kitty. Meow, meow. Your leg all better? Yeah. Look at my happy Christmas kitty. Oh, you didn't like that, huh? You were cranky.